It should have had a tail. It didn't. That absence, that silence where physics promised noise was the first alarm. A comet from another star, 3I, Atlas, had just skimmed past the sun and behaved like nothing we've ever seen. Most comets announce themselves with drama-bright tails arcing across the void, shedding billions of tons of dust and gas as sunlight tears at their frozen skin. They hiss, they bloom, they leave fingerprints of light. But 3I, Atlas didn't. It simply passed through a faint sphere of light, featureless and quiet, like a thought half-formed. For weeks, astronomers waited for the familiar signs: the jet, the coma, the radiant tail that always follows when ice meets heat. And for weeks, nothing appeared. By the 30th of October 2025, the object reached perihelion, its closest point to the Sun, just 0.9 astronomical units. At that distance, the heat should have vaporized its surface. Calculations from NASA's Jet Propulsion Laboratory confirmed a radial acceleration of 1.1 times 10 to the power of -6 AU per day squared, caused by the pressure of material blasting away from the nucleus. That acceleration doesn't happen without violent outgassing, and outgassing doesn't happen without a tail. The numbers are precise, unambiguous. The object lost over 13% of its total mass, roughly 4 billion tons of material. 4 billion tons of dust and vapor that, by every known law of celestial thermodynamics, should have painted the sky. Instead, the images returned blank, only a blur surrounded by stillness. When the first frames arrived from Mars orbit, no one quite believed them. The Tianwen-1 probe, its primary mission long complete, had turned its cameras toward an intruder from beyond the stars. From 18 million miles away, it captured the sharpest view ever recorded of an interstellar object and found nothing that fit the expectation. No streaming filament of ice, no spectral trail, just a luminous knot, self-contained, drifting against the darkness. ESA's Mars Express and the Trace Gas Orbiter confirm the same thing from different angles. A coma without direction, as if the comet refused to shed identity into the solar wind. Across observatories on Earth, telescopes recalibrated, searching for dust scattered along its orbit. They found none. It was as if the debris had dissolved into equations instead of space. In science, silence is rarely neutral. It means either absence or discovery. The more they looked, the stranger the quiet became. At first, some proposed geometry, maybe the tail was hidden, pointed directly at or away from us, invisible by alignment. Others blamed instrumentation, glare, or timing. But the data didn't lie. The non-gravitational acceleration was real. Something was pushing 3I Atlas outward from the Sun. We could measure the force precisely. We just couldn't see it. That contradiction, measurable thrust without visible, cause turned routine observation into mystery. A. Comet is a story told by heat. Frozen volatiles turning to vapor, sunlight sculpting chaos. Yet here was a body from interstellar space rewriting the grammar of comets entirely. No shimmering exhale, no luminous tail, no radiant confession of what it was made of. Only motion steady, deliberate, unornamented. Astronomers compared brightness curves, ran simulations, and stacked exposures until the data blurred into static. The result was the same. The nucleus brightened slightly as it neared the Sun, then dimmed again, leaving behind no spectral trace of dust. Not invisible, non-existent. That word haunted the reports. Somewhere in that absence, meaning began to collect. Was it simply a coincidence, a natural outlier behaving at the edge of known physics? Or was there something purposeful in the restraint, an economy of motion too clean to be random? They couldn't say. They only knew that by every calculation, 3I, Atlas, was the most massive and fastest interstellar object ever recorded. About 5.6 kilometers wide to 30 billion tons in mass, moving at 58 kilometers per second, 129,000 miles per hour, big enough to hold mountains, fast enough to circle Earth in 18 minutes, and yet almost invisible in behavior. For the scientists tracing its path, the experience felt dissonant, like hearing music with every note removed but one. They expected spectacle. Instead, they received subtlety. They expected noise. Instead, precision. Every model predicted chaos near perihelion. Instead, the comet moved as if under guidance, its trajectory smooth, unperturbed, following a curve too perfect to seem accidental. Not controlled, but composed. And in that composition, a new kind of awe took shape. Not the loud wonder of explosions and flares, but the quiet recognition that nature might express power through absence as much as presence. As 3I, Atlas drifted away from the sun, the tail that never appeared became its defining feature. The missing made it memorable. For centuries, humans had read comets as omens fire writing across the sky. This one left no handwriting, only the blank page. Astronomers from JPL to CNSA logged the data, cautious in language but clear in implication. A hyperbolic trajectory, a measurable acceleration, inconsistent with gravity alone, and a conspicuous lack of the luminous dust that should explain it. In spreadsheets and simulation maps, the void itself became the signal. And that's where this story begins, not with light, but with what refused to shine. Because sometimes, the loudest phenomena in the universe are the ones that stay silent. Mars saw what Earth could not. While our planet turned blindly beneath the glare of the sun, another world, smaller, quieter, rust-coloured, opened its single mechanical eye and captured what no telescope on Earth ever could. The first close images of an interstellar visitor in history. On November 5th, 2025, the Tianwen-1 orbiter transmitted a small batch of black and white frames to mission control in Beijing. 18 million miles separated the spacecraft from its target, a distance vast enough to swallow the entire inner solar system, yet close enough for the camera to resolve something never seen before. A fuzzy sphere, suspended in a vacuum, radiating nothing but reflected sunlight. No stream, no flare, no chaos. China's space agency, CNSA, called it a technical success. But behind closed doors, scientists stared at the data in disbelief. It wasn't supposed to look like this. To understand the magnitude of that moment, imagine the challenge. Tianwen-1 had been orbiting Mars for over 4 years. Its instruments were tuned for landscapes, valleys, dunes, ice caps. The high-resolution imaging camera, HIRIC, was designed to photograph a planet's surface from low orbit, not to track an object smaller than a city, darker than asphalt, and moving faster than any natural body ever recorded, all while tens of millions of kilometers away. Retargeting that system meant rewriting its entire operation mode. The spacecraft had to orient itself toward a point of light, dimmer than a star, maintain sub-arc-second precision in its pointing, and time each exposure with Mars' own orbital motion. In essence, a robotic geologist turned its gaze from rock to infinity, and it succeeded. The frames came back sharp enough to identify a coma several thousand kilometers wide, yet even there, no sign of a tail. It was as if 3I, Atlas, refused to perform the role physics had written for it. On Earth, sunlight and geometry conspired against observation. From our perspective, the comet had passed behind the Sun during its closest approach, invisible to every ground-based telescope, even Hubble and Webb. The universe had staged its most enigmatic act in plain daylight, hidden in blinding radiance. But Mars had the angle. From its offset orbit, Tianwen-1 saw around the Sun's glare, peering into the corridor of space Earth could not reach. It witnessed what we missed. For the first time in human history, another planet became our proxy eye. Through its lens, we saw the visitor not as rumor or reflection, but as presence. When the data reached ESA's headquarters days later, scientists cross-checked the results with their own platforms. The Mars Express and the Trace Gas Orbiter, TGO, both had been conducting atmospheric studies, not astrophotography yet. Even their instruments confirmed the same profile. A compact, self-contained light signature, no dust plume, no ion tail. 3 separate spacecraft, 3 nations, 1 impossible observation. In a joint release, the European Space Agency and CNSA published the image metadata, exposure time, focal length, thermal readings, and solar angles. Every number is aligned. Nothing had been missed, nothing miscalibrated. The absence wasn't an error. It was a fact. The images themselves looked almost trivial, grainy dots adrift in grayscale. But within those dots lay an epochal shift. For decades, interstellar objects were theoretical ghosts, predicted, unseen, intangible. Oumuamua and Borisov had been glimpsed only from afar, both long gone before any probe could aim a camera. 3i, Atlas changed that. For the first time, a human-made instrument met something from another star, not face-to-face, but close enough to touch with light. In Beijing, one mission engineer reportedly whispered, "We pointed at infinity, and it pointed back." No one answered. The room was filled with the quiet hum of data transfer and something else: reverence. The Global Astronomy Network responded instantly. Data packets from Mars were mirrored to JPL, ESA, and the National Astronomical Observatory of China. Teams decompressed the raw telemetry, applied denoising algorithms, and reconstructed the object's morphology. Result: a faint halo, uniform, perfectly centered. No asymmetry, no directional flow, no sign of dust reflecting sunlight anisotropically, the definitive indicator of a tail. Even after perihelion, when residual outgassing should have produced a visible streak, the space around 3i, Atlas, remained unnervingly clean. The object had apparently shed billions of tons of material, yet the surrounding vacuum looked untouched. It was as though the act of release erased itself. To some, this was beauty. To others, a warning. The European Planetary Science Conference convened an emergency session that week. One physicist described it as a perfect contradiction between thermodynamics and aesthetics. Another simply said, "It's like watching evaporation without vapor." The Tianwen images became the most downloaded scientific files of the year. Thousands of independent analysts pored over them, professionals, amateurs, AI vision systems searching for artifacts or overlooked features. None found evidence of a tail, not even a whisper of a plume. Every pixel reaffirmed the same impossible calm. By the end of November, the headlines softened. What began as shock turned to contemplation. This wasn't just about one comet behaving strangely. It was about perspective, how much of reality depends on where we're standing when we look. Earth, blinded by sunlight, saw nothing. Mars, in shadow, saw everything. The universe hadn't changed, only our angle had. That realization sank in slowly, almost philosophically. That knowledge itself might be a matter of geometry. That truth, like light, who could depend on distance and alignment? In the weeks that followed, the phrase Mars saw what Earth could not spread through the scientific community like a quiet mantra. It reminded everyone that discovery is often a matter of patience and position of being somewhere unexpected at the right pi. A moment. For Tianwen 1, that moment had come by chance, but what it captured reshaped the boundaries of chance itself. From 18 million miles away, across the orbit of another world, humanity had finally looked directly into the face of something born beyond our sun and found it staring back with absolute stillness. No tail, no roar of physics, only the steady light of an enigma. And in that faint reflection, for the first time, the cosmos felt close enough to touch. The data doesn't lie, but it whispers. Its truth hides not in volume, but in vibration, quiet numbers rippling through silence. After Tianwen 1-second images, the world turned to the numbers, because photographs can deceive, but math does not. At least, that's what we tell ourselves. The first full data set from NASA's Jet Propulsion Laboratory, JPL, arrived in early November. Position vectors, radial velocities, acceleration curves, each plotted against the solar gravitational model. And there it was, a persistent offset, tiny, consistent, undeniable. 3i, Atlas wasn't moving exactly where gravity said it should. The object was accelerating outward, pushed by something invisible. The deviation measured 1.1 times 10 to the power of -6 astronomical units per day squared along the Sun-object axis, and a transverse component of 3.7 times 10 to the power of -7 AU per day squared, perpendicular to it. To anyone fluent in orbital mechanics, those numbers are thunder in code. They mean one thing: non-gravitational acceleration. In comets, such motion is caused by outgassing jets of vaporized material, venting from the surface as sunlight warms frozen ices. Each molecule escaping the nucleus acts like a miniature thruster, imparting tiny impulses that accumulate over time. The effect is subtle but measurable, and here it was not only measurable, it was dramatic. By integrating the acceleration over the perihelion arc, Scientists calculated that 13% of the comet's total mass must have been expelled in a matter of days. For a nucleus roughly 30 billion tons, that means nearly 4 billion tons of gas and dust vanished into space. 4 billion tons, enough to fill every skyscraper in Manhattan with ice and erase them again in vapor. And yet, not a single gram of that disappearance showed up where it should have, in the light. ESA analysts double-checked JPL's figures using independent astrometry from the Mars Express and Gaia databases. The conclusion was identical, the force was real. No instrument glitch, no computational rounding error, no solar pressure anomaly. The comet had been pushed. The question was by what? In a late-night call between Pasadena and Darmstadt, one mission engineer summarized the problem in a single sentence. If it's venting, the sky should be glowing. But the sky was dark. Outgassing is one of the most predictable processes in cometary physics. You can model it with elegance, pressure gradients, sublimation coefficients, solar flux equations. Each variable sings its own line, and together they form the expected melody. Heat, vapor, acceleration, tail. 3i. Atlas played the first 3 notes and skipped the rest. It moved like a comet, but looked like an asteroid. It accelerated like a gas, but appeared like a stone. It whispered contradictions. To visualize it, imagine a candle whose flame exerts pressure, nudging the candle backward, but the flame is invisible, and the candle never melts. You can feel its recoil, but never see the fire. That was 3i Atlas. Astronomers plotted brightness against time, searching for the typical correlation. As outgassing increases, luminosity surges, but 3i Atlas's light curve remained eerily flat. The physicist said it was screaming. The photons said it was silent. Theories multiplied like constellations. Maybe the gas it expelled was pure CO2, transparent to visible light. Maybe the particles were electrically charged and swept away before forming a tail. Maybe the mass loss was internal, venting beneath a crust so dense that dust never escaped. Each explanation seemed plausible until tested. Each one unraveled under the weight of its own equations. By mid-November, the consensus was uncomfortable. We don't know why it moves like this. Somewhere between the decimals, humility began to grow. Because the data wasn't loud, it was patient. It didn't demand belief. It simply pointed toward absence and waited for us to listen. Astronomers reran their orbital fits. They compared 3i Atlas with Oumuamua, 2017, and Borisov, 2019, both earlier. Interstellar objects had shown peculiar accelerations, though smaller whispering predecessors to this new enigma. The pattern was forming, faint but rhythmic, like a pulse beneath the noise. Maybe this wasn't an anomaly. Maybe it was a language. In scientific papers, the tone stayed neutral. Phrases like requires further investigation and may indicate non-standard material composition mask the quiet astonishment between the lines. But among researchers, the conversations turned speculative. What if the outgassing isn't chemical? One asked. What if it's something we can't detect radiation pressure from a reflective structure or sublimation of exotic ices invisible in our spectral range? Someone else said, what if the equations are right but the interpretation is wrong? The data didn't shout answers, it invited interpretation. It whispered possibility. In January 2026, when 3i Atlas would already be receding toward the outer dark, the accumulated trajectory data would still hold the same riddle. Acceleration without evidence, mass loss without debris, motion without message. The universe had performed an equation, and all we could read was the remainder. But silence doesn't mean nothing is happening. It means something is happening too precisely for our senses to catch. Maybe the expelled matter was molecularly invisible. Maybe the jets were directional, aimed sunward, masking themselves in glare. Maybe the object had evolved a surface so black, so non-reflective, that it devoured its own evidence. Whatever the truth, the implications were the same. Our models, the comfortable, time-tested architectures of physics had found their edge. And beyond that edge lay quiet. In conference halls and observatories, a new phrase began circulating. The data doesn't lie, but it whispers. It became both caution and creed. Because the universe doesn't always announce revelation with spectacle. Sometimes It speaks through subtleties, through numbers that refuse to balance, through absence mistaken for error. And those who listen closely enough may find that mystery isn't the opposite of knowledge. It's the beginning of it. 4 billion tons vanished. And no one knows where it went. By early November, the numbers had already drawn a map of absence. JPL's calculations said the comet had lost mass equal to the weight of a mountain range. The acceleration made sense only if something vast had been expelled. So telescopes turned to the sky, expecting to see the evidence ribbons of dust, a faint streak of gas, the soft shimmer of debris dispersing into the void. They saw nothing. In Italy, the Virtual Telescope project under Gianluca Marsi aligned its optical arrays toward the coordinates provided by JPL. Across the night sky, the faint speck of 3I, Atlas appeared as a dim fuzz barely above background noise. Even with long exposures, the object refused to reveal a tail. No dust plume, no scattering, just a nucleus wrapped in an indecipherable halo. At the same time in Spain, the Naves Observatory performed a parallel observation. Their images matched Marsis, an unremarkable grey sphere, sharp at the core, fading cleanly into black. 2 independent telescopes, 2 countries, 1 shared silence. The question forming among both teams was the same. Where did the debris go? To verify their instruments, the astronomers ran a control. They turned their telescopes toward Comet Lemon, a routine solar system visitor observed just 2 days earlier, on November 3rd, 2025. Its orbit and solar distance were nearly identical. Its brightness is comparable. The difference, Lemon behaved exactly as the textbooks promised. On screen, Lemon blazed with the classic shape of a cometary tail, a long, radiant plume stretching millions of kilometers away from the sun, perfectly aligned with the solar wind. Light scattered off fine dust, revealing curves of motion like brushstrokes on black canvas. The contrast between Lemon and 3I, Atlas, was not subtle, it was surgical. 2 comets, 2 near-identical conditions, one performed. Physics. The other denied it. At the Italian observatory, someone printed both images, Lemon on the left, 3I, Atlas on the right, and pinned them to the wall. Under the fluorescent light, the difference looked absurdly simple. One image was alive, the other austere. One was chaos, the other silence. It was as if the universe had drawn its own before and after diagram of comprehension. In the comparison, every expectation of cometary behavior became visible by its absence. The dust tail is missing, the gas coma is too compact, the light polarization is inverted, even the faint debris trails that normally linger in long exposures were nowhere to be found. Something had stripped. 3I, Atlas, clean. Some proposed that the debris existed, but was hidden too faint, too small, or too transparent to register. Others suggested it had been expelled at an angle invisible from Earth's vantage. But the geometry didn't support that. ESA's post-perihelion models placed the comet well past solar conjunction. Its tail, if present, should have been visible against the dark sky. There was nothing to hide it, no solar glare, no atmospheric interference, no camera error. Only void. The term dustless outgassing began appearing in conference notes, a contradiction in itself. A comet that outgasses without dust is like a storm without wind, a fire without smoke. The more they examined, the deeper the tension grew. When 3I, Atlas, passed perihelion, it should have released billions of particles following predictable ballistic trajectories. Astronomers searched for those particles along their orbits, scanning for faint reflected light as the fragments trailed behind. Even at the most generous detection thresholds, they found no debris field. If 4 billion tons had been ejected, it had either dispersed beyond visibility in record time or never existed in visible form at all. That's when the discussion shifted from the visible to the philosophical. What if the debris isn't gone? One researcher asked, but transformed? The idea sounded abstract, but the math hinted at it. If the expelled material were composed of elements that sublimated directly into ionized gas, no solid dust, no reflective grains, it would vanish almost instantly after release, invisible to optical wavelengths. Possible? Perhaps. But on this scale, billions of tons in days, such behavior would require chemistry we'd never documented in any comet before. Another theory invoked radiation shielding, a surface so dark and thermally resistant that only invisible gases could escape through microvents, leaving no visual trace. The data didn't confirm it, but didn't refute it either. And in that grey zone, imagination took hold. Still, scientists are cautious storytellers. They turned to verification, not metaphor. Every image from Martian Naves was reprocessed using differential photometry. When aligned against known background stars, the residuals revealed nothing but the same stubborn stillness. Noise? Yes. Signal? No. To make sense of the void, they turned once again to control data from Lemon. Overlaying both light curves, they expected small deviations. Instead, they found entire philosophies separating them. Lemon's brightness fluctuated with its tail activity predictable, rhythmic. 3i, Atlas, remained steady, monotonic, almost indifferent. If Lemon was a symphony, 3i, Atlas, was a held note, unwavering, unresolved. Somewhere in this comparative silence, a realization began to bloom. Maybe 3i, Atlas, wasn't defying physics. Maybe it was teaching us the limits of visibility. Our instruments record reflected photons, not intent. Our models predict behavior based on patterns, not exceptions. But what happens when an object follows rules we haven't written yet, when it obeys physics beyond the resolution of our sensors? The images from Italy and Spain became emblems of that question. One pair of frames showing everything expected of the universe, and another showing everything it can still surprise us with. Weeks later, as the data circulated, a quiet phrase appeared in several research abstracts. The absence of evidence is not evidence of absence, but of inadequacy. It was both admission and invitation, a recognition that the mystery wasn't in the comet itself, but in the narrowness of our sight. 3. Atlas had shed something. We measured its departure. We watched for the dust and saw none. And in that blank, the question multiplied. Was the debris ever visible? Was it ever meant to be? Because if the universe wanted to leave us a message, it wouldn't need to write it in light. Sometimes, it writes in what light refuses to show. It came from another star, yet it flew in our plane. Every solar system has its own geometry, a kind of cosmic fingerprint. Our planets travel along a shared disk called the ecliptic plane, the flattened remnant of the cloud that birthed them. All their orbits Earth, Mars, Jupiter, even the dwarf outliers lie within a few degrees of that invisible sheet. It's the rhythm of our system's origin, the way dust once spun into order. But for anything born beyond the sun, anything interstellar, there is no reason to follow that plane. No cosmic rule binds the galaxy to our geometry. Rogue objects should arrive from every possible angle, plunging in from above, slicing sideways, veering in from the poles of the solar system like stones skipping off water. That randomness is what makes them interstellar. That's how Oumuamua and Borisov arrive steep, unpredictable, indifferent to our orbital choreography. 3i, Atlas didn't. When its trajectory was first plotted through the OrbFit database, a quiet shock rippled through the analysts. The inclination, the tilt between its path and our ecliptic plane was measured at just 5 degrees. 5. Not 50. Not 20. 5. So close to flat that its orbit it could be projected directly over the planets. Paths, like the transparent sheet laid perfectly atop the solar system. Too coincidental, one researcher murmured. Another replied, coincidence is the universe's native language. Still, the odds resisted dismissal. Statistically, the chance of an interstellar object arriving within 5 degrees of the ecliptic is about 0.2%, roughly 1 in 500. Unlikely, but not impossible. Once, maybe twice in a lifetime of observations. But this wasn't just geometry. It was choreography. Using Gaia DR3 data, astronomers reconstructed the inbound vector, the direction and galactic coordinates from which 3i, Atlas, entered our solar neighborhood. It wasn't random. It slid precisely along the plane where Earth, Venus, and Jupiter orbit, retrograde to their motion as if threading a needle between worlds. To visualize it, imagine standing above the solar system. looking down at the orbits of all the planets like concentric rings around the Sunday. Then imagine a line slicing through those rings not at an angle, but within them almost perfectly horizontal, like a shadow gliding across a record's grooves. That was 3I Atlas's path. If the solar system were a dinner plate, most interstellar visitors fall like crumbs from above or below. This one skimmed the rim. For astronomers accustomed to randomness, that precision felt uncanny. A few joked about cosmic courtesy, as if the object had chosen the polite route through traffic, but others frowned at the math. A pattern so flat, so aligned, so elegantly coincidental, demanded either extraordinary luck or some mechanism of guidance. Of course, science resists anthropomorphism. Nothing chooses its path. Yet the flatness remained an irritant in the data, a small persistent thorn of improbability. To test for bias, teams ran a series of Monte Carlo simulations, generating thousands of hypothetical interstellar trajectories. Only 2 out of every 1,000 random paths aligned within 5 degrees of the ecliptic. 2 out of 1,000. That's what 3I Atlas had done by accident, if accident was still a word big enough to contain it. The simulations didn't stop there. They modelled perturbations by stellar gravity, galactic drift, and interstellar drag. None of them produced an orbit this clean, this cooperative. Some researchers tried to rationalize it. Maybe the object originated from a star system aligned similarly to ours, a parallel plane, another disk tilted just right. Maybe its long journey through the galaxy had gradually flattened its trajectory. Or maybe it was simply statistical fate. With enough dice rolls, even the rarest sequence eventually appears. But those explanations came with caveats. A parallel ecliptic among stars would be an extraordinary coincidence in itself. Galactic drift tends to randomize, not align, and eventually only matters in infinity, not in the brief, 3-object history of interstellar discoveries we've made so far. 3 visitors, Oumuamua steep, Borisov angled, 3I, Atlas flat. The pattern, if any, was evolution toward order. In a paper drafted at ESA's Operations Center, one scientist phrased it delicately. 3. I Atlas exhibits an anomalously low orbital inclination, inconsistent with the expected isotropic distribution of interstellar arrivals. Translation: it's too flat to be random. A colleague scribbled in the margin, maybe the universe isn't isotropic, maybe it's conversational. The note was meant as a joke, but it lingered. In press releases, agencies avoided poetry. They spoke of statistical outliers and alignment anomalies. But beneath the neutral phrasing lay an unspoken question. How does something born from another star find the same plane that defines ours? If space were truly random, we should have seen countless directions of arrival. But the first few visitors we've met seem considerate. They enter our system not with chaos, but with precision. One astrophysicist described it like this: it's as if these objects know where the table is set. No one quoted her, but everyone remembered the metaphor. By mid-November, orbital simulations were refined to millimeter accuracy. The inclination stayed steady at 5 degrees, no matter how far the models extended. The object hadn't drifted into alignment by chance, it had arrived aligned. Every perturbation traced back to the same near-perfect plane. From a probabilistic view, this was the first anomaly the crack that would soon widen. It wasn't proof of anything beyond curiosity, but it planted the seed of suspicion that maybe the universe sometimes arranges its dice before throwing them. If 3I Atlas had plunged in at a wild angle, it would have been forgotten as another cosmic visitor. Instead, it entered quietly, gracefully, as though following the grooves of a song only it could hear one perfectly in tune with the rhythm of our solar system. Coincidence, perhaps, but in science, every coincidence is a door, and this one had just begun to open. It fired toward the sun. That should be impossible. Comets obey light. They're sculpted by it, pushed and shaped by the relentless radiation streaming from our star. Every grain of dust, every molecule of gas released from their surface is forced away from the sun by solar wind and radiation pressure. That's why tails always point outward away from the glare. Always. Until July 2025, when 3I Atlas turned and did the opposite. The discovery came from a cluster of observatories across Europe, Japan, and South America. Through the clear winter skies of the southern hemisphere, telescopes began to record an unfamiliar pattern. A faint jet of material, not streaming away from the sun as expected, but directly toward it. A thin filament of brightness, angled sunward, visible across multiple instruments and wavelengths. At first, no one believed it. It had to be an illusion, a trick of perspective known as an antitail. Antitails sometimes occur when a comet's orbit and Earth's line of sight overlap, making a regular tail appear to point the wrong way. But the geometry of this case didn't fit. ESA's Solar System Dynamics team ran simulations using Gaia DR3 and ESO's Paranal Observatory viewing data. The angles didn't align. Even after adjusting for parallax, light scattering, and orbital inclination, the jet was still aimed into the sun. It wasn't optical confusion. It was physical defiance. In late July, the European Southern Observatory, ESO, and Japan's Aerospace Exploration Agency, JAXA, compared notes. The Subaru telescope in Hawaii confirmed what Paranal had seen: a sustained, narrow emission line, measurable over several nights, oriented sunward within a few degrees. By August, the phenomenon was consistent across 4 independent observatories. No known comet had ever behaved this way. Solar pressure alone should have obliterated any jet facing the sun within seconds. Yet 3I, Atlas, maintained it for weeks. To quote the JAXA report, observed jet persists counter to expected radiation pressure vectors. No known natural mechanism reproduces this orientation. In other words, the object was doing something nature had no rule for. Scientists began searching for loopholes. Could it be a magnetic interaction, localized eruptions at the nucleus, complex rotation, creating a temporary illusion? Every model was tested, every variable tuned. The result, still inexplicable. If the nucleus had rotated rapidly enough to fling gas sunward before centrifugal force redirected it, the light curve would have shown rapid flickering, but it didn't. If magnetic fields were responsible, the emission spectrum would have revealed ionization, but it was neutral. If gravitational perturbations from a nearby planet had twisted the jet's path, the trajectory data would show oscillation. It was linear. The jet's behavior was steady, clean, precise. It was as if something inside, 3I, Atlas, was controlling its own release. In the technical bulletins that followed, language became cautious. Terms like non-traditional outgassing vector replaced the simpler phrase, a jet aimed at the Sunday, but the meaning was unchanged. An interstellar object was behaving as though the sun itself were the target. ESA's image processing team tried to model what the jet would look like from different vantage points. From Mars' orbit, it appeared faint but distinct, a spear of light piercing the glare. From Earth's perspective, hidden behind the sun, it would have been invisible. Another alignment that seemed almost considerate. By early August, the phenomenon faded. The jet dissolved, leaving no residual debris, no flare, no increase in brightness, just motion steady, unbothered, accelerating outward. But the data stayed, and when plotted against time, something remarkable emerged. The sunward jet corresponded precisely with the period of measured acceleration detected by JPL and ESA. The comet was being pushed outward at the exact moment it appeared to be ejecting material, inward, a paradox of motion force without visible cause, thrust without recoil. One physicist compared it to a swimmer pushing toward the current and somehow being carried away by it faster. The phrase anomaly 2 began circulating internally among mission teams. The first anomaly had been geometry improbable alignment. The second was intent behavior contradicting physics. Skeptics warned against anthropomorphism. They reminded everyone, nature has no intentions, only mechanisms we don't yet understand. But the unease remained, because even when stripped of metaphor, the fact refused to dissolve. Something had projected material toward the sun against the fundamental direction of solar pressure, and sustained that behavior long enough for multiple observatories to confirm it. That is not an error. That is an event. Avi Loeb, in a brief interview that month, said softly, "Nature is the most efficient engineer we know, but efficiency rarely contradicts itself. When it does, we should listen." He wasn't claiming artificiality, just humility. If the universe writes in paradox, we shouldn't rush to translate. In September, the compiled dataset solar jet coordinates verified by ESO and JAXA, was released to the public archives. Researchers everywhere downloaded the files, each running their own spectral analyses, their own motion vectors, their own attempts to prove the impossible wrong. None succeeded. The anomaly held. By then, the news cycle had moved on, but within the quiet corridors of the scientific community, the unease had taken root. The first anomaly flat arrival had felt improbable. The second, a sunward jet, felt intimate, as though the object had, for a moment, looked back at the star that warmed it. For all our equations and telescopes, we still navigate the cosmos through metaphors. We call comets messengers, though they carry no words. We call their trails tails, though they don't chase anything. And now, faced with one that turned to face the sun, we reached again for language. Not proof. Just poetry to hold what data could not. Because when the universe breaks its own rules, sometimes the only response left is wonder, the kind that feels like fear softened by awe. It wasn't supposed to be this big, or this fast. When JPL finalized its trajectory models, one statistic stood out like a flare against darkness. 3. Atlas wasn't just another interstellar visitor. It was the largest and fastest ever recorded, a paradox of scale and speed. Most interstellar objects we've met so far have been small, fragile, temporary cosmic debris flicked into our system by gravitational accidents. Oumuamua in 2017 measured barely 200 meters across. Borisov in 2019, a little over half a kilometer. Both behaved like shards, tiny messengers, easily influenced by solar forces. But 3I, Atlas, was different. Its nucleus measured nearly 6 kilometers wide, the width of Manhattan from river to river, a mountain of rock and ice moving through space. According to ESA mass estimates, it weighed around 30 billion tons, more than 1,000 times heavier than Borisov, and millions of times more massive than Oumuamua. And it wasn't drifting, it was racing. The JPL Horizons database logged its speed at 58 kilometers per second, roughly 129,000 miles per hour, relative to the Sun. At that velocity, it could circle Earth in just 18 minutes. A steel bullet the size of a city, crossing the solar system with the patience of light and the energy of annihilation. Objects that large aren't supposed to move that fast. And objects that move that fast aren't supposed to be that large. The universe, however, had decided otherwise. To understand how improbable this is, imagine throwing a rock so hard that it escapes not just your hand, not just Earth's gravity, but the entire pull of the Sun, and then keeps going, crossing the galaxy for millions of years. That's what interstellar velocity means. But large bodies rarely achieve it. The energy required to eject something 5 kilometers wide from its home star system is astronomical. It would need a cataclysm, a near collision with a gas giant, or the gravitational slingshot of a dying sun, or something even more extreme. Such events can happen, yes, but the odds of them sending a large, cohesive, intact object toward us are minuscule. Statistically, the chance of observing a body, both this massive and this fast in our lifetime, is less than 0.1%, 1 in 1,000. And yet, here it was. In early analysis sessions, some scientists compared 3I, Atlas, to Borisov, the only other interstellar comet observed behaving roughly by the book. Borisov was bright, icy, and small, evaporating gracefully under solar heat. But 3I, Atlas, had none of Borisov's fragility. It absorbed sunlight and barely changed. Where Borisov melted, Atlas endured. Where Borisov curved, Atlas sliced through the void like geometry itself. It was, as one ESA engineer wrote, less a comet, more a statement. The mass-to-velocity ratio puzzled everyone. If an object is that large, its inertia should dominate, making it less responsive to gravitational tugs or solar radiation. Yet 3I, Atlas, was accelerating just enough to be noticed, defying the gravitational model by a measurable margin. How could something so heavy behave so delicately? Some speculated it might be hollow, a fractured shell masquerading as a solid core. Others theorized it was composed of ultralight material, porous as pumice, its density far lower than expected. But the photometric data argued otherwise. The light curve suggested density, solidity, and uniform reflection, not hollowness. If it were a rock, it would be a perfect one. And perfection rarely occurs in nature. In September, ESA and JAXA co-published their findings, highlighting the improbability of 3I, Atlas's mass-speed combination. In a single paragraph, buried between equations, the paper admitted what everyone already suspected. The conjunction of high velocity and substantial mass indicates an ejection scenario not well represented in current astrophysical models. Translation: we have no idea how something this big got moving this fast. Theories surfaced, each more exotic than the last. Perhaps it had been launched from a collapsing binary system flung outward by the combined gravity of two suns. Perhaps it was the remnant core of a destroyed planet, its mass compacted and hurled into galactic exile. Or perhaps, and this one, quietly unsettled everyone, it wasn't an accident at all. Because scale and speed together suggest something else: purpose. If a civilization ever wanted to send something across the stars, they'd need it to be durable, massive enough to survive radiation, and fast enough to cross light years before the sender was forgotten. In other words, they'd build something exactly like 3I Atlas. That idea wasn't published, but it was whispered. Still, the official narrative stayed conservative. Natural object. Anomalous but explainable. Science must resist romance. And yet, the story itself felt romantic. A cosmic messenger, enormous and ancient, slipping into our solar system like a memory too vast to hold. Every new image confirmed its size. Every trajectory fit confirmed its speed. And with each confirmation, unease deepened. Because in the long timeline of astronomy, patterns matter. 3 interstellar objects were observed. 3 are wildly different in form, size, and behavior, each one stranger than the last, as if the cosmos was slowly turning up the volume on a message we haven't yet learned to decode. For now, scientists focused on what they could measure. Diameter, 5.6 kilometers. Mass, 3 times 10 to the power of 10 tons. Velocity, 58 kilometers per second. Probability is less than 0.1%. Those numbers don't dramatize, they hum. And in their hum lies something sacred, the sound of our ignorance being measured with precision. Because for all our equations and telescopes, we are still children listening at the edge of a vast conversation. And 3I, Atlas, huge and swift and utterly indifferent, might just be the echo of a sentence we were never meant to hear but did. It passed every world with eyes except ours. From the start, 3I, Atlas behaved as if it knew where we were looking. Each planet it approached had a camera waiting. Each encounter perfectly timed. And then when it reached the moment of greatest visibility, it vanished, hidden behind the sun. Astronomers call this geometric coincidence. Statisticians call it improbable. Poets might call it something else. Between September and October 2025, 3I, Atlas traced a route through the inner solar system that read less like a random flyby and more like a tour. On its inbound trajectory, it passed within observation range of Mars, Venus, and Jupiter, each home to operational orbiters. Each had its sensors trained on the void. Each captured it. At Mars, the Tianwen-1 orbiter and Mars Express recorded high-resolution images. At Venus, ESA's solar orbiter detected brief light scatter, matching the comet's predicted coordinates. Near Jupiter, long-range instruments from JUICE logged a fleeting reflection, faint but consistent with the expected trajectory. It was as though the object had threaded a path through every functioning probe humanity had beyond Earth. And then, when it reached perihelion, the closest point to the Sun, where brightness should have peaked, it positioned itself directly behind the Sun from Earth's line of sight. For 3 critical weeks, every telescope on our planet was blind. By the time it reappeared, the show was over. The silence was deliberate, or felt that way. ESA and CNSA both maintained detailed mission logs. When those logs were cross-referenced in November 2025, the timeline formed a pattern so clean it seemed staged. Sept 310, Mars encounter, active orbiters in view. Sept 27, Venus proximity, solar orbiter data confirmed. Oct 10, Jupiter observation window, faint spectrographic return. Oct 30, perihelion, invisible from Earth, blocked by the Sun. 4 alignments, perfectly sequential. the probability of an interstellar object intersecting 3 planetary orbits with active spacecraft and then reaching solar conjunction at Earth's blind spot. Approximately 0.005%, about 5 in 100,000. Random, yes. But probability doesn't comfort easily when coincidence looks like design. When orbital simulators reconstructed the path, the visuals were hypnotic. Against the dark model of the solar system, 3I Atlas's trajectory traced an elegant arc, grazing Mars, brushing Venus, looping past Jupiter's gravity well, then sliding behind the Sun before emerging again into open space. Every turn, every timing, smooth to the point of artistry. If you didn't know better, you'd think it was following a script. Scientists, though, they are cautious with wonder. They passed the geometry for errors. Perhaps the alignment was only apparent a trick of projection. But simulations accounting for orbital inclination, observation windows, and spacecraft positions showed the same result. The alignments were real. ESA's internal summary phrased it like this: trajectory passes through multiple observation vectors of active probes before entering the Earth-Sun conjunction. Coincidence, probability, statistically negligible. In plainer language, it flew past every camera we had then hid. By late October, a strange unease took hold. The object had chosen, accidentally or not, the one path that allowed it to be witnessed just enough to be undeniable and unseen, just long enough to remain mysterious. It wasn't that 3I Atlas wanted attention. It managed exposure like an expert in shadows. A journalist from Le Monde Science called it a celestial magician's trick. Now you see it, now you don't. The metaphor was dismissed by scientists, but quietly, some agreed. Because what are coincidences, if not the universe's sleight of hand? Back at JPL, mission controllers plotted where Earth would have been had our orbit shifted just a few weeks earlier. Had the object arrived a single month sooner, its perihelion would have been visible from multiple observatories on Earth. Instead, it crossed the Sun's near side exactly when our planet was positioned to be blinded. A gap of 37 days, that's all it took to turn a visible event into a hidden one. Bad timing, one engineer said. Another corrected him, or perfect timing. CNSA's mission telemetry showed something equally curious. During its approach to Mars, 3I, Atlas's position relative to Tianwen, one produced an imaging angle almost identical to the one that captured it weeks later during perihelion exit. The symmetry was uncanny. The same probe that opened humanity's first, close view also unknowingly captured its last. In one mission log, a CNSA scientist wrote, "It began and ended with Mars. No one edited it out." In December, as astronomers began compiling the year's data for publication, a subtle narrative emerged in the margins, a recognition that chance alone was beginning to strain believability, not in the sense of conspiracy, but in the sense of choreography. One researcher in Darmstadt wrote, "When independent probabilities multiply, coincidence approaches structure." It was a careful way of saying what everyone felt. That 3I Atlas was following a rhythm we didn't set. Statistically, the anomalies were still within possibility. But possibility isn't comfort, it's camouflage. The object had traced a path through every lens except the ones on our own planet, and in doing so, it left behind a pattern almost too poetic to ignore. Mars saw it first. Earth saw it last. The Sun hid it in between. It avoided our gaze not through secrecy, but through geometry. And in that geometry, some saw intention, while others saw instruction. That maybe the universe reveals itself only to those who aren't the center of the story. When the final orbital simulations were rendered, and the path resembled a looping filament, a glowing thread, weaving through planets like beads on an invisible string. Some called it a coincidence of celestial mechanics. Others whispered choreography. Either way, the numbers remain. 5 in 100,000. That's the probability. But to those who watched the dance unfold, it didn't feel like chance. It felt like a conversation conducted in motion, where the only rule was timing and we were one beat late. It gleamed like metal where ice should be. By late October 2025, the pictures had gone still, but the spectra kept talking. While the world fixated on brightness and tails, the deeper secret hid in the wavelengths, in the faint fingerprints of light, scattered off 3I Atlas surface. That's where chemistry whispers what the eye cannot see. When CNSA and ESA's Mars Express transmitted their joint spectroscopic data, analysts expected the usual cometary signatures: water, carbon dioxide, cyanides, maybe traces of silicate dust. Instead, the graphs returned something alien in its familiarity. Peaks appeared where iron should have dominated, but the ratios were reversed. Nickel, not iron, who was in control. The INTA Spectral Lab in Madrid confirmed it first. The nickel-to-iron ratio was inverted, an exact mirror of what every natural comet and asteroid has shown for centuries of observation. Across the solar system, iron outweighs nickel roughly 10-1. Here, nickel exceeded iron. The numbers were clean, the data consistent across instruments. Noise wasn't the culprit. The comet was genuinely nickel-rich by orders of magnitude. At first, that might sound trivial. After all, both metals often coexist. But metallurgy, whether cosmic or human, follows predictable recipes. Iron condenses more readily in stellar nurseries. Nickel forms later, in smaller fractions. An inverted ratio suggests something unnatural, either a birthplace with wildly different chemistry or a process that refined the material after formation. To the scientists at INTA and CNSA, it looked less like a comet and more like a forged alloy. The word industrial appeared in one lab memo, then was immediately crossed out. No one wanted to be the first to say it aloud, but the implication was unavoidable. In the entire catalogue of known comets, none had ever displayed a composition this metallic, this dry, this deliberate. Because it wasn't just the metals, it was the absence of water. Comets are called dirty snowballs for a reason. Their cores are typically 70 to 80% ice, the rest dust and rock bound together by cold. When sunlight hits, the ice vaporizes, driving jets that sculpt the tail, the signature that defines them. But Mars Express infrared spectrometer found only 4% water by mass in 3I Atlas. 4. That's less than what a volcanic rock holds in trapped crystal moisture. At that level, 3I Atlas wasn't a comet. It was a stone pretending to be one. The term rock-like object entered ESA's internal documentation paired with a quiet question mark. The 4% figure was double-checked, cross-referenced, and confirmed again by independent labs in Beijing and Darmstadt. Same result, no error bars big enough to explain it away. A body 5 kilometers wide, flying through interstellar space, yet almost completely devoid of the frozen volatiles that define cometary life. No water, no methane, no ammonia in quantities that made sense, and still, it emitted acceleration, consistent with violent outgassing. The contradiction deepened. How does something that isn't icy behave as though it's boiling? To visualize the problem, imagine a desert rock suddenly behaving like a kettle. Heat it, and instead of glowing, it moves propelled by something you can't see, powered by fuel that isn't there. That was 3I Atlas. Spectral labs built models to simulate alternate explanations. Could the metallic surface hide internal ices, sealed beneath a crust? Possible, but not at 96% purity. Could the spectra be fooled by reflective dust, masking the water signal? Unlikely. The signal-to-noise ratio was too strong. No matter how they turned the data, the conclusion held. The comet was dry, metallic, and strangely uniform. When ESA and CNSA combined their datasets, another anomaly emerged, a disproportionate abundance of nickel cyanide, a compound rare in nature, even rarer in comets. On Earth, nickel cyanide appears in electroplating and high-temperature industrial processes. In the cosmos, it should barely register. Yet 3I Atlas showed ratios hundreds to 1,000 times higher than any recorded cometary sample. Someone in the meeting room said it out loud. If this were a lab sample, we'd call it engineered. The room fell silent. Nobody wanted that quote on record. In scientific papers that followed, the phrasing softened. Words like non-standard metallicity and anomalous condensation history replaced the uncomfortable adjectives. But the undertone remained. This object wasn't just compositionally strange, it was methodically strange. ESA's chemistry team noted that nickel, unlike iron, resists corrosion and handles extreme temperatures better, precisely the qualities required for durability under stellar heat. If you wanted to build something to survive a close pass by a star, nickel would be the logical choice. Coincidence? Perhaps. But patterns have gravity too. The combination of anomalies began to feel less like errors and more like architecture data points snapping together into implication. High mass, high velocity, flat trajectory, sunward jets, metallic surface, minimal ice. Each detail improbable alone, together, statistically absurd. Harvard's Avi Loeb wrote in a brief commentary, "If 3I Atlas were a natural comet, it would be the driest, heaviest, most metal-rich comet in history. If it were artificial, it would be the most subtle machine ever built." He didn't mean it literally, but the sentence lingered in the minds of those who read it. For now, the conservative explanation prevails. 3I Atlas formed in an extraordinarily hot, metal-rich region of another star system, perhaps near a young sun, whose heat baked away volatiles before the object was ejected into interstellar space. That theory fits the data, mostly. But even then, one question remains unsolved. If it were born dry, what powered the acceleration we measured? Without ice, there is no gas. Without gas, there is no thrust. And yet, 3I Atlas moved. It is both solid and transient, dense yet responsive, stone that behaves like steam, a contradiction orbiting at 58 kilometers per second. By the end of October, INTA's final report summarized the metallic riddle in one line. Spectra suggest a body composed predominantly of nickel compounds and silicates with trace water. Ice is less than 4%. Resembles industrial alloy more than cometary aggregate. That's the data. It's not speculation. It's not fiction. It's my measurement. And measurement, like truth, doesn't care what we believe. 3I Atlas was a rock without water, a comet without ice, a mirror without reflection. And as it turned back toward the void, its spectrum faded, leaving us with one last paradox. The more precisely we measured it, the less sense it made. Light bent the wrong way, and the past whispered back. By November 2025, the list of impossibilities surrounding 3I Atlas had grown into a small constellation of its own, but three final anomalies, light, signal, and surge, completed the pattern. Each is strange enough alone. Together, they defied coincidence entirely. Anomaly 7, the light that polarized backward light. Polarization is one of the quiet truths of physics. When sunlight scatters off a surface, dust, ice, or rock, it becomes partially polarized. The degree and direction of that polarization reveal surface texture, composition, and particle size. Every comet ever observed falls neatly into predictable ranges. Low polarization at small angles, rising near 90 degrees, then fading. 3I Atlas broke that rule. The CNRS polarimetry database logged readings from multiple observatories, showing extreme negative polarization. The light wasn't just scattering oddly, it was inverting. Instruments recorded a pattern opposite to every known comet in the record. To visualize it, imagine shining a flashlight at a mirror and watching the beam twist itself into shadow. That's how the data felt light, refusing to behave like light. This wasn't an error. Independent measurements from ESA's Solar Orbiter and the French Pic du Midi Observatory confirmed the same inversion across filters. The numbers didn't flinch. Something about 3I Atlas's surface, perhaps its metallic skin, perhaps something more exotic, was twisting polarization backward, bending reflection into absorption. In a joint CNRS-CNSA report, the phrasing was clinical yet unsettling. Polarimetric inversion, unprecedented in cometary physics. Surface composition or structure unknown. Translation: we don't know why light turns negative here, only that it does. Anomaly 8, the angle of memory. The wow. Connection. While the photometry teams wrestled with optics, another group noticed something geographical, or rather, cosmic. The entry vector of 3I Atlas, plotted through galactic coordinates, aligned within 9 degrees of the 1977 wow. Signal direction, the mysterious narrowband radio burst detected by the Big Ear radio telescope in Ohio nearly half a century earlier. The signal had come from a region near the constellation Sagittarius, a direction rich with hydrogen clouds but poor in explanation. For decades, it remained the most famous unsolved whisper from the stars, a 72-second spike that read 6 EQUJ, 5 on paper, and never repeated. No serious scientist claimed a connection, but when the entry coordinates of 3I, Atlas, were overlaid with the WOW vector, the alignment was startlingly close. 9 degrees, a narrow sliver on the cosmic sphere, not identical, but near enough to draw the eye and raise the pulse. When Cornell University cross-referenced Arecibo's archival pointing logs with the 2025 inbound path, the numbers aligned within tolerance for what they called directional coincidence. Probability of such overlap? Roughly 1 in 10,000. Statistically ignorable. Emotionally unforgettable. Because what are the odds that our loudest unanswered signal and our strangest interstellar visitor would share the same patch of sky, divided by decades, united by direction? One astrophysicist joked darkly, "Maybe we got the message first, and the sender arrived late." It wasn't quoted publicly, but it echoed quietly in observatory hallways. Anomaly 9, the surge blue light from nowhere, the final anomaly, was brightness, a surge that broke even the last semblance of pattern. Most comets follow a simple rule. As they near the sun, they brighten predictably according to their albedo and sublimation rate. A 2x increase in solar flux yields roughly a 1.5x rise in brightness. Stable, calculable, boring. 3I, Atlas defied the graph. As it neared perihelion, its luminosity spiked 12-fold in a matter of days, an explosive surge unmatched in cometary records. But the surprise wasn't just intensity, it was colour. The surge came not in red or yellow, as expected from heating dust, but in blue. A cold electric blue wavelength shifted, unnatural, almost spectral. The JUICE mission spectrometer picked up a distinct blue spectral shift of several nanometers not due to Doppler velocity, but intrinsic emission. The CNSA spectral log matched the reading, a narrow spike around 475 nanometers, consistent with excited metal ions, the same region where ionized nickel radiates under energy stress. Nickel again. The same metal that dominated its surface now glowed under excitation, as though the entire body had pulsed with internal current. Observers described it as a flash without explosion, energy, visible but silent, power with no aftermath. And just as quickly as it appeared, it faded, leaving the comet darker than before. Each anomaly on its own might have been explained, but taken together, negative polarization, WOW-aligned trajectory, blue spectral surge, the pattern turned unnerving. Light, signal, and motion all bend toward coherence. It was as though the object wasn't just passing through space, it was communicating through it, not in language, but in coincidence. The kind of coherence that feels accidental only until it happens 3 times in a row. At the CNRS headquarters in Paris, one researcher scrawled a note in the margin of his report. The object reflects less, remembers more. No one could prove what he meant, but everyone understood it, because by then, 3I, Atlas, had ceased to feel like an event. It felt like an answer, waiting for the right question. By mid-November, the anomalies were officially logged, the data archived, and the scientists exhausted. Nothing about 3I, Atlas fits the categories built to hold it. Every attempt to contain it in equations only deepened the silence around it. The universe had, once again, obeyed its favorite law that knowledge expands faster than understanding. And yet, for all the confusion, there was a growing calm, the kind that comes not from resolution, but recognition, that perhaps these coincidences were never meant to prove anything, only to remind us that light and memory are not separate things. Because when an object bends light backward, aligns with an echo from 1977, and glows blue without heat, it isn't asking to be solved. It's asking to be noticed. 4 billion tons, gone without a trace. Every story we tell about comets begins with loss. They approach the sun, they burn, they shed, they vanish. Their tales are the handwriting of their destruction, beautiful, predictable, luminous. But 3I, Atlas wrote nothing. It passed the furnace, survived, and left behind a blank page. When ESA and CNSA finalized their post-perihelion datasets, they confirmed what every earlier image had whispered. No tail, no gas, no debris field, not even the faintest scattering that normally betrays evaporated dust. By every measurement, 4 billion tons of material had been expelled. Yet the Tianwen-1 images and ESA's post-perihelion tracking showed space as clean as before, the encounter pure black behind a single point of light. This wasn't just an absence, it was a contradiction made visible. The missing tail forced scientists to revisit every prior anomaly. The flat trajectory, the sunward jet, the metallic composition, the reversed polarization. Each of them had seemed improbable on its own, but together they now orbited one greater mystery. How could a comet lose that much mass without leaving anything behind? The physics demanded consequence. Every action in the cosmos, every spark, every exhale of gas leaves a trace. Here, nothing, no plume, no echo. The universe had made a subtraction and hidden the remainder. At ESA's mission control in Darmstadt, they projected the latest Tianwen-1 image sequence onto a large wall, frame by frame. They followed 3I, Atlas, as it receded from the sun. Its brightness dimmed, its halo shrank, and then, at the point where a comet's tail should have flared, the surrounding pixels stayed perfectly black. One physicist compared the pattern to a candle burning with invisible fire. It was, in essence, an event without evidence, a physical process that erased its own footprint as it happened. Some proposed that the ejected material consisted of superheated ions that became transparent under solar radiation. Others argued for nanometric particles, too small to scatter, visible, light. But even those explanations demanded at least some infrared signal, some measurable afterglow. Mars Express found none. ESA's infrared spectrometer scanned the region weeks after the passage. The void returned a perfect baseline. No dust, no residual gas, no cooling signature. A cosmic crime scene scrubbed clean. One analyst described it bluntly: if 4 billion tons of material left the nucleus, it disappeared into equations, not space. The conclusion shook the foundations of cometary physics. Outgassing, fragmentation, and sublimation. All of it depends on visibility. The entire discipline is built on light. But here, the light refused to speak. And if the most basic law of observation, that to act is to be seen, fails, what else might fail with it? By now, the scientific community had divided into camps. The conservative group insisted there must be an optical or geometric explanation yet undiscovered. Perhaps the tail existed but extended in a plane directly along our line of sight, so perfectly aligned it blended with the object's glare. But simulations disproved it. The chance of such alignment persisting through weeks of motion was infinitesimal. Others whispered something different. That maybe the absence wasn't an error, it was design. Not intention, necessarily, but structure. Maybe 3I, Atlas, wasn't radiating energy outward like a normal comet. Maybe it was recycling it, internalizing the outflow, behaving like a closed system, a machine that expels without dispersing. The idea was too speculative for publication, yet the math kept inviting it back. When ESA's post-perihelion tracking merged with CNSA's photometric data, another small miracle surfaced. The comet's overall brightness decreased smoothly, linearly, and too perfectly. Ordinary comets flicker as they shed material, their light curves pulse with chaos. 3I. Atlas faded like a dimmer switch being turned, controlled, even, predictable. If you plot its decline on a graph, the line forms a clean exponential decay, an almost musical descent. One researcher said, "It's as if it followed an equation we didn't write." That smooth fading became the signature of Anomaly 10, the missing tail that shouldn't be missing. It wasn't absence through randomness. It was an absence with rhythm. Somewhere in that rhythm, the earlier mysteries began to feel less isolated. The flat arrival, the sunward jet, the metallic shell, the negative light, all of it seemed to orbit this single realization. Perhaps 3I, Atlas, wasn't breaking rules. Perhaps it was expressing them in a language we hadn't yet translated, because when energy leaves a system invisibly, it doesn't vanish, it transforms. And transformation, at a cosmic scale, can look like silence. At an ESA debrief in mid-November, a senior scientist summarized what everyone had come to feel. If the missing tail is real, it's not an error in our observation. It's an error in our definition of visibility. The room went quiet, because that statement didn't just describe a comet. It described us. In science, we measure what we can see, we explain what we can measure, and everything else we call mystery. But 3I, Atlas, forced a more humbling thought that maybe reality doesn't vanish when it becomes invisible. Maybe it continues just outside the spectrum where our instruments end. That realization didn't bring comfort, only perspective. Because if 4 billion tons can disappear into dark equations, what else might be happening right now, unseen, unmeasured, perfectly real? As 3I, Atlas moved away from the sun, growing fainter each day, the paradox it left behind began to glow brighter than its body ever had. A comet without a tail, an absence brighter than presence, a silence louder than light. And in that silence, science itself seemed to pause, not in failure, but in reverence. Coincidence has limits, and numbers remember where wonder forgets. By the time the 10th anomaly was logged, the data no longer resembled a collection of mysteries. It looked like a pattern so statistically absurd that it forced even the most skeptical minds to pause. The quiet unease of scientists turned into something colder, cleaner, mathematics. Because math doesn't believe, it just counts. Each anomaly, taken alone, might be excused. A flat orbit here, a strange jet there, a missing tail, a metallic surface, a reversal of light. Everyone could be a rare event unlikely, but within the tolerance of a universe built on variance. But together, the math began to whisper rebellion. If each had less than a 1% probability, their combined occurrence wasn't just unusual. It was statistically impossible in ordinary nature. Not metaphorically impossible, numerically impossible. At Harvard's Institute for Theory and Computation, Avi Loeb's team began running multiplicative probability trees, the same technique used to calculate compounding odds in cosmology. Each branch represented one anomaly, each fork one chance in 100. 10 branches later, the product line reached 1 in 10,000. A single point in a sea of zeros. If the universe rolled dice that way, we shouldn't have seen 3I, Atlas. Not once. Not like this. And yet, we did. Loeb called it anomaly clustering, the phenomenon where independent improbabilities converge in one event, collapsing random distribution into a pattern. He used the same logic once applied to Oumuamua, when acceleration, shape, and reflectivity combined into a probability too low to ignore. But 3I, Atlas made Oumuamua look simple. 10 deviations, all verified, all cross-confirmed by international observatories. 10 separate rolls of cosmic dice, each landing on the edge. This wasn't luck, it was a structure hiding in statistics. ESA's analysts were less poetic but equally unsettled. In internal notes, one wrote, "If this were a laboratory result, we'd rerun the experiment to look for bias. But the universe doesn't rerun." So they turned instead to reanalysis. Data pipelines were rebuilt from scratch, spectral readings reprocessed, angles recalculated. Still the same numbers, still the same improbability. Eventually, skepticism gave way to something quieter. Acceptance not of answers, but of limits. Probability, after all, is a language of humility. It doesn't predict, it measures surprise. And by that measure, 3I, Atlas, had broken the scale. If an event with a 0.01% likelihood occurs, it demands either an explanation or an expansion of the model. Either nature is stranger than we thought, or our thought is smaller than nature. In his brief Harvard preprint, Loeb wrote, "Statistical outliers do not necessarily indicate intent, but they do require attention. The cosmos may be less a random sea and more an archive of organized accidents." He didn't claim aliens, or artifacts, or design. He claimed curiosity. He claimed the right to look again. At ESA's Data Summit, a different kind of conversation emerged, not about physics, but philosophy. One researcher asked, At what point does improbability stop meaning rare and start meaning deliberate? No one answered. Because science, bound by discipline, avoids the word deliberate. But behind their silence, the math kept talking. Every model they built, cometry, thermal, magnetic, the geometric still produced the same improbabilities. Flat orbit, 1 inch 500. Sunward jet, 1 inch 1000. Size and speed, 1 inch 1000. Timed encounters, 1 inch 20,000. Metallic dryness, 1 inch 500. Light reversal, signal alignment, spectral surge, each rarer than the last. Multiply them, even conservatively, and the universe seems to be performing a miracle. Not once, but repeatedly. To frame it differently, imagine tossing a coin 10 times and watching it land on its edge every single flip. You'd call it trickery. But the cosmos has no hands to cheat, with only patterns too deep for probability to explain. That was 3I, Atlas, a coin balanced on its own motion, refusing to fall into heads or tails. The mathematical post-mortem became almost spiritual in tone. After weeks of recalculation, one analyst said softly, "Numbers don't lie, but they can reveal that our reality might." It wasn't cynicism. It was awe, the kind that comes when formulas stop being barriers and start becoming mirrors. Because in the clean logic of improbability, something beautiful hides. The reminder that existence itself is already an outlier. Every breath, every orbit, every thought we have is statistically impossible. Yet here we are, calculating. Maybe that's what 3I, Atlas, came to show, not alien intent, but mathematical empathy. That improbability isn't an error, it's identity. Still, the numbers stand. 10 anomalies, each verified, each improbable. Combined likelihood is less than 1 inch 10,000. It's not a conspiracy, it's statistics. And statistics, when stretched to breaking, become something else. Poetry written in decimals. At the end of ESA's report, a single line appeared under further study. The pattern of anomalies may indicate an unrecognized category of interstellar object. That was the official phrasing. But off record, one scientist rewrote it in the margin, or an unrecognized category of purpose. They didn't mean design. They meant meaning, that sometimes the math itself is the message. Because when numbers stack beyond probability, when logic trembles under its own proof, and when silence produces symmetry, the universe might not be mocking us. It might be introducing itself. Belief divides us. Data doesn't care. By the time the 10th anomaly was logged and the probabilities collapsed to 1 in 10,000, one voice stood again at the center of the debate. Avi Loeb, the Harvard astrophysicist who had already walked this path before. He'd been here once, with Oumuamua, years earlier. Now, with 3I, Atlas, the déjà vu was palpable. The same pattern. An object behaving just outside the bounds of known physics, data too precise to dismiss, too strange to explain. The same question, what if it isn't natural, and the same resistance. Don't say that word. Loeb never claimed certainty, he claimed attention. He claimed that the possibility itself deserves courage. In an interview that November, when asked if he thought 3I, Atlas, might be artificial, he leaned back, smiled, and said softly, "It's not about belief. It's about observation." That sentence rippled through the community like a quiet shockwave, not because it was provocative, but because it was true. Science, after all, isn't built on consensus. It's built on an anomaly. Every leap forward begins with a measurement that shouldn't exist. Still, the backlash was instant. Mainstream astrophysicists accused Loeb of romanticizing uncertainty. Some said he was chasing headlines, not truth. Others feared his questions would invite pseudoscience into the conversation. But Loeb had data. Not metaphors, data. He cited the metallic composition, the non-gravitational acceleration, the inverted light polarization, and the statistical impossibility of all 10 anomalies coinciding. He wasn't claiming aliens. He was claiming logic. If it looks unnatural and behaves unnaturally, the burden of proof isn't on asking why. It's on proving it isn't. That line appeared in one of his essays, half challenge, half plea. What unsettled many wasn't the suggestion of intelligence, but the precision of his reasoning. Because Loeb never argued for belief. He argued for the removal of fear from curiosity. He compared our era of astronomy to the pre-Copernican world, when the idea of Earth not being the center of everything felt heretical. Back then, he said, truth was a social risk. Now, it's an academic one. He wasn't wrong. In lecture halls and online forums, scientists debated him with a mix of admiration and discomfort. Some called him reckless, others unnecessary. But no one could refute his numbers. Loeb's team at Harvard published a short analysis mapping every 3I Atlas anomaly against historical comet data. The resulting chart looked like an inverted bell curve. 900 comets behaving predictably, one sitting far off on its own island of improbability. That outlier was Atlas. The visual alone was haunting one dot disconnected from every other, like an exile from normal physics. When journalists asked Loeb if he thought that dot represented technology, he answered carefully, "Technology implies intent. I'm only saying we should not dismiss intent before it's disproven." His critics called it speculation. But Loeb countered with a simple question. If it were artificial, how would we know? Silence followed, because no one had an answer. No instrument is designed to detect intention. Telescopes measure motion, not motive. Spectrometers read composition, not context. And yet, the entire history of discovery from fire to DNA has been driven by asking if what we see might mean more than it appears. So what if meaning itself was measurable, hidden in data like static between frequencies? At a Harvard colloquium that month, Loeb stood before a slide titled, "Rethinking the Null Hypothesis." He argued that assuming natural origin for every anomaly might itself be biased, the cosmic version of saying, "Nothing to see here." He said, "The safest way to stay ignorant is to only ask safe questions." In that room of mathematicians and astronomers, some nodded, some frowned. But all took notes, because even those who disagreed couldn't deny the resonance of what he said next. Curiosity isn't rebellion, it's their responsibility. Outside the lecture halls, the public conversation shifted tone. News outlets stopped framing 3I, Atlas, as just another comet, and began asking, what makes this one different? The word artifact started appearing, cautiously, in editorials. Not as a claim, just as vocabulary. Because once you learn something might be built rather than born, the mind refuses to forget it. Meanwhile, the data continued to stand unshaken. All 10 anomalies remained verified. No sensor malfunction, no observational bias, no calibration errors are large enough to erase them. The numbers had spoken, and they were indifferent to belief. ESA's internal conclusion was sober. The observational dataset remains internally consistent, yet externally inexplicable. The kind of sentence only science could write, one that sounds calm, while quietly rewriting the definition of reality. For Loeb, it wasn't vindication. It was fatigue. Had been here before dismissed, debated, defended. But something about 3I, Atlas, felt heavier, bigger, as if this time the mystery itself was tired of being ignored. When asked what he hoped the discovery would change, he paused before answering. Maybe nothing. Maybe just the courage to admit we don't know. Then, almost as an afterthought, he added, "Every civilization has two choices, fear its sky or study it." That line made its way into countless articles and presentations that winter. Not as dogma, but as a reminder that doubt isn't the enemy of science, complacency is. And so, whether 3I, Atlas is a rock, a relic, or a riddle, Loeb's legacy in this story isn't belief, it's permission to wonder without apology. Because sometimes reason itself is the most spiritual act of all. Not everything that reaches us was meant to. By late November, the storm of data had settled into a strange, reflective quiet. 10 anomalies, one object, no explanation. And somewhere between disbelief and acceptance, a new thought began to form. Maybe this wasn't communication. Maybe it was a coincidence with the structure. Not all information is transmitted. Some is overheard. For months, scientists had treated 3I Atlas as if it were speaking through motion, through light, through improbable timing. But what if the silence itself wasn't absence? What if it were syntax? What if we had stumbled across something not intended for us at all? A conversation between the universe and itself, caught mid-sentence. It's a humbling idea, that we might be eavesdropping on creation. When astronomers reconstructed the object's trajectory, the elegance was unmistakable. Its path was deliberate, even if directionless, weaving through planetary orbits, mirroring old signals, obeying celestial geometry like choreography. Yet no clear purpose emerged. It left no payload, no beacon, no repeatable pattern, just an impression of design without a designer. In one internal ESA debrief, a physicist wrote in the margins, "The silence is structured." The phrase stuck, because that's what it felt like: order without message, rhythm without language, pattern without point. In information theory, there's a concept called structured noise. It describes randomness that appears too organized to be purely chaotic, not meaningful, but not meaningless either. Like the pattern of waves on a shore or the pulse of static when you tune between radio stations. Somewhere in the interference, the signal leaves a ghost of its shape. 3i. Atlas was that ghost data with form but no intent. It wasn't calling. We just happened to be listening. At Harvard, Loeb's team had begun using the word resonance instead of message. Resonance implies response not sent or received, just shared. A bridge between frequencies. Perhaps the object didn't need to say anything. Perhaps its mere existence was the echo. That shift from message to resonance changed everything. It moved the narrative from paranoia to participation. From someone sent this to something happened and we heard it. In December, a joint ESA-CNSA conference gathered to review what the data had ultimately meant. The tone was less defensive now, more contemplative. A scientist from Darmstadt summarized it best. Maybe we're not the audience. Maybe we're just standing where the sound passes through. No one argued. For once, humility felt like progress, because if the universe is truly vast and ancient, then perhaps most of what exists isn't directed toward us. We are listeners in a field of overlapping signals, every star emitting its own dialect of radiation and gravity. 3i. Atlas might have been just one more echo. Not an announcement, not an artifact, but an accident aligned so perfectly with our instruments that it became a mirror. And mirrors, after all, don't speak. They reflect. At the Paris Observatory, researchers began modelling the event in a new way, not as a trajectory, but as a pattern of attention. They plotted every discovery, every observation, every gap in our visibility, and found that the rhythm of discovery itself mirrored a kind of heartbeat, peaks and silences alternating like breath. The universe, they joked, had a pulse. But no one really laughed, because beneath the humour was a dawning intuition. Maybe awareness itself was part of the design. Maybe 3i, Atlas, didn't appear to tell us something, it appeared to remind us to notice. The concept resonated far beyond astronomy. Philosophers, theologians, poets, they all found metaphors in the silence. One wrote, "Perhaps the message isn't that we're being watched, but that we're capable of watching." Another compared it to a candle seen through glass, the flame invisible, the light unmistakable. Presence without origin. That was the paradox of 3i, Atlas, a phenomenon that refused both belief and denial, hovering in the space between explanation and wonder. By the end of the year, the term structured silence entered the official literature. It was Loeb himself who coined it during a seminar. The absence of evidence, he said, can sometimes be the evidence of absence, and other times the evidence of pattern. 3i, Atlas may be the latter. No grand claims, no proclamations of life or intent, just the quiet recognition that some things organize reality without reason, and that recognizing that organization might be the closest we ever come to understanding. There's an old saying in radio astronomy, the cosmos doesn't whisper, it resonates. We only hear it when our instruments happen to vibrate at the same frequency. Maybe that's what happened here. Not a transmission, but a coincidence of harmony, a brief overlap between the trajectory of an object and the awareness of a species that happened to be listening at the right moment. We didn't receive a message. We received a reminder that the universe is constantly speaking, whether or not it's speaking to us. As the last data from Tianwen-1 faded from telemetry, the final images showed nothing unusual, just a dim dot against infinite black, shrinking into the background noise. No revelation, no encore, no proof. But in that quiet fading, something unquantifiable remained. A pattern, invisible but undeniable. A silence that felt arranged. Maybe it wasn't a message, but maybe, just maybe, it was still meant to be heard. Maybe the universe has been speaking all along. We just built instruments for noise. By the time 3I, Atlas, faded beyond the reach of every telescope, the story had stopped being about a comet. It had become a mirror for us, for how we see, how we listen, and how much of reality we mistake for randomness. Every model we've built of the cosmos begins with an assumption. We expect comets to have tails. We expect acceleration to come from outgassing. We expect noise to be meaningless. But what if expectation itself is the distortion? What if what we call noise is simply language we haven't yet learned to read? For centuries, science has taught us to filter the universe, to strip away the irregular, to smooth the data until it fits our definitions. We call that progress. We call that precision. But every act of filtering hides something. 3I, Atlas broke that habit. It refused to fit. Every filter failed. Every model fell silent. And in that silence, we heard ourselves, a species trained to detect only the familiar, blind to the possibility that the unfamiliar might be intentional. When ESA presented the final analysis to the world, the conclusion was careful. Observed anomalies remain unexplained within current physical frameworks. But beneath that sterile phrasing lay an invitation not to declare mystery, but to redefine understanding. Because what if this wasn't about discovery at all? What if it were about training attention, a test not of technology, but of perception? Across the sciences, a subtle shift began. Astrophysicists started asking whether their algorithms designed to suppress background noise might be erasing patterns that weren't noise at all. Machine learning researchers began experimenting with models that listened differently, searching not for repetition, but for coherence within chaos. Even philosophers of science re-entered the conversation, reviving a question long buried under data. Does understanding mean explaining or recognizing? Maybe it's both. Maybe explanation is only one dialect of understanding. Recognition might be the other. One night, at Harvard, Loeb was asked during a panel discussion what he thought 3I, Atlas, had really taught us. He paused, then smiled faintly. We've been so focused on detecting messages, he said, that we forgot how to interpret silence. The audience didn't applaud immediately. They just sat there, absorbing the weight of it. Because for once, the silence after a question felt like an answer. The truth is, science has always been built on failure. Each discovery born from the ruins of what we thought was certain. The orbit of Mercury broke Newton. Quantum mechanics broke reality. Now, perhaps, 3I, Atlas was breaking our pattern recognition. It was reminding us that the universe doesn't owe us legibility. It only offers presence. And presence, unmeasured, still counts as knowledge. In laboratories and observatories around the world, researchers began revisiting old data sets not to prove new hypotheses, but to listen again, to unlearn, to see if other moments of noise might have been subtle songs, dismissed too quickly. The new mantra became, search for pattern, not perfection, because nature doesn't polish its miracles, it hides them in rough edges, in irregularities that feel like error until they repeat. And repetition, as 3I Atlas taught us, is just one way of speaking. The silence that followed its departure didn't feel empty. It felt like calibration, the pause before hearing differently. When Tianwen-1 transmitted its last telemetry ping, one engineer noted that the signal curve showed a faint harmonic, a tiny oscillation in amplitude that no one could identify. Just interference, they said. Or maybe not. Maybe every silence has texture, every void a fingerprint. We're only just learning to listen with enough humility to notice. In a quiet essay published later that year, Loeb wrote something that felt like closure. The most important discoveries aren't found in data, but in the willingness to doubt the filter that collected it. When you remove the bias of certainty, even the noise begins to make sense. It was the kind of sentence that reads like science and prayer at the same time. And so, a new question emerged among those who had followed the entire saga. What if 3I, Atlas, wasn't a messenger at all but a mirror for the way intelligence recognizes intelligence? Not a signal from the outside, but a prompt from within, a reminder that awareness is measured not by what we know, but by what we're willing to admit we don't. It's easy to think that meaning must arrive as order, as pattern, as sound. But maybe meaning is the willingness to listen before there's anything to hear. Maybe our instruments are fine, it's our vocabulary that's small. Maybe the next discovery won't come from a louder signal, but from deeper attention. Because sometimes, the universe doesn't announce itself. It just waits for you to stop filtering the noise. In the end, 3i, Atlas, left us with no answers, only better questions. And that may be the truest kind of communication there is. Not information transferred, but perception transformed. It didn't change physics. It changed our posture toward mystery. What if the greatest act of intelligence isn't solving what's strange, but refusing to call it strange at all? History doesn't repeat itself, but the cosmos does rhyme. In the long memory of observation, 3 visitors now mark our threshold. 3 interstellar bodies, each carrying a fragment of the unknown. Oumuamua, Borisov, and now 3i, Atlas. To most, they're entries in a catalogue. To those who looked closer, they form a sentence. A progression, a rhythm, a quiet pattern too human to ignore. Each one arrived from beyond the stars. Each behaved as though obeying a rule we hadn't written. Each whispered a new verse in the same unfinished poem. Oumuamua came first in 2017, slender, silent, and brief. It tumbled like a shard of metal and accelerated without explanation. Its light curve defied natural form. Too thin, too smooth, too deliberate. The world met it with excitement and dismissal in equal measure. It was the opening note one that ended before we could decide what it meant. Borisov followed 2 years later, blazing through with all the comfort of normalcy. A comet, icy, bright, behaving mostly as comets should. It was as though the universe had offered reassurance. See, nothing strange here, only the familiar returning. Yet even Borisov's composition hinted at excess. Its ice is richer, its molecules stranger than any local object. And then came 3i, Atlas, combining both contradictions, the structure of one, the enigma of the other. A synthesis of silence and spectacle. Together, they formed a triad: the shard, the flame, and the mirror. Astronomers began to notice the pattern not in numbers, but in feeling. Each event arrived like a refrain returning in a new key, different notes, same melody. The cosmos, it seemed, was composing, not repeating, but evolving. We once thought interstellar visitors would all look alike, fragments of the same universal chemistry, ruins of the same cosmic accidents. But these 3 objects refused uniformity. They were singular, distinct, yet undeniably connected by timing, rarity, and improbability. Oumuamua, the impossible shape. Borisov, the perfect comet. 3i, Atlas, the contradiction incarnate. Not repetition, but rhyme. At ESA's year-end symposium, one slide captured it best. A simple graphic showing 3 orbits, each crossing our solar system like separate brushstrokes on the same canvas. The presenter said quietly, "If randomness ruled absolutely, we wouldn't see rhythm. But the universe loves rhythm." The room fell still, because rhythm implies memory, and memory implies meaning. Patterns like these have always unsettled us. We trust chaos because it comforts us with its indifference. But when coincidence begins to sound like cadence, we grow uneasy, because cadence feels personal. It feels like participation. In the centuries before telescopes, people looked at the stars and heard stories. Now, armed with data, we still hear stories. Only this time, they arrive coded in orbital parameters and light curves instead of myth. Maybe the ancients weren't wrong. Maybe they just lacked spreadsheets. When Loeb was asked if he saw a connection between the 3 interstellar objects, he hesitated. "If the universe is an orchestra," he said, "then 3i, Atlas, is the third movement, not repetition, but variation." That phrasing, third movement, stuck. Because every symphony builds on earlier themes, each echo shapes the next note until meaning emerges through difference. Oumuamua startled us. Borisov reassured. Us, 3i, Atlas transcended both. showing that familiarity and strangeness can coexist in a single body of light. In probability theory, 3 data points define a pattern. Beyond that, coincidence becomes a trend, and trends hint at law. So maybe this wasn't an accident. Maybe our corner of the galaxy happens to sit along a corridor where wanderers drift through like pilgrims passing a temple door. Or maybe these 3 are all fragments of one long event, a cosmic migration unfolding over centuries, each visitor a chapter in a story written across light years. The math doesn't confirm it, but the rhythm feels undeniable. For many scientists, the realization carried a new kind of humility. We once thought discovery was about finding the unknown. Now, it feels more like learning to recognize the familiar in what was never ours. Because even anomalies have lineage. The same forces that birthed Oumuamua also birthed us. The same galactic tides that carried 3I, Atlas, through our system once swept through the dust that made our oceans. Connection isn't mystical. It's gravitational. And gravity, at its heart, is the universe's way of remembering itself. When the final reports on 3I, Atlas, were archived, a closing note appeared on the first page of the ESA file. Comparative analysis suggests the possibility that interstellar visitors exhibit non-random distribution of composition and trajectory. If confirmed, such a structure implies coordination on scales exceeding current cosmological models. The language was cautious, but between its lines lived a quiet wonder that even randomness might have rhythm, and that perhaps, on cosmic scales, chaos itself keeps time, because what are we to the universe if not another variation? Another rhyme in its unfolding poem. Every atom in our bodies once drifted between stars. Every thought we have is built from recycled starlight. We are participants in its meter, not spectators to it. Maybe that's why each new interstellar object feels less like an invasion and more like a reunion. They're not visitors, they're verses returning to their source. So the question isn't why they came, but why were we ready, only now, to notice the rhythm? The cosmos doesn't repeat, it echoes, and every echo is an invitation to listen closer to the space between arrivals, where the rhyme continues, quietly, waiting for its next line to find us. Sometimes, the universe changes not the world, just one life. By December 2025, the headlines had faded. The public had moved on, and the news cycle turned. But in one quiet corner of Harvard's inbox, a single message arrived that reminded everyone why curiosity matters. It came from Chile, written in Spanish, sent by a man named Eduardo Varela. He wasn't a scientist. He worked at a vineyard near Valparaiso, repairing irrigation pumps and teaching his daughter English in the evenings. His email was short, almost hesitant. Professor Loeb, you don't know me, but my daughter does. She read about 3I, Atlas, every night. She says it's the first time she's felt the universe breathing. Next year she will study astrophysics. Thank you for making her believe that science is still alive. No theories, no numbers. Just gratitude, quiet and human, like the faint echo of something enormous made intimate. Loeb read it twice, then once more aloud to his students. In the midst of all the debate, the data, the statistical infighting, here was something unarguable. The story had reached someone, not through proof, but through wonder. And that, he thought, might be the purest form of truth science can offer. Her name, he later learned, was Lucia, 18 years old, the first in her family to apply to university. When journalists asked her later why she'd chosen astrophysics, she answered simply, because 3I, Atlas, didn't make sense. And I want to live in the questions, not just the answers. It wasn't a quote you find in textbooks, but it captured something the data never could, how mystery itself becomes oxygen for those who dare to breathe it. Lucia's story spread quietly among researchers, the kind of story shared in hallways, at conferences, in the long pauses before presentations. Because after months of arguing over probabilities and trajectories, here was a reminder of why they were all still doing this. Why does humanity even bother to look up? For her, 3I, Atlas wasn't an anomaly. It was a bridge between curiosity and belonging. When she looked at the Tianwen-1 images online, she didn't see data noise. She saw proof that not knowing could be beautiful. There's a moment in every scientist's life when discovery stops being about achievement and starts being about awe. For some, it's the first image from a telescope. For others, it's the silence between questions, the hum that says, keep listening. For Lucia, it was a comet that refused to behave. She told her father she liked that 3I Atlas broke rules, that it didn't care about categories or expectations. That reminded her of people who aren't believed until they prove themselves by existing anyway. Her father wrote those words in his second email to Loeb. She says the comet is her favourite kind of truth, the kind that survives disbelief. That sentence, Loeb later said, meant more to him than any citation count. Because science often forgets its emotional dimension, the quiet courage of curiosity, the willingness to live inside uncertainty. But Lucia hadn't forgotten. She had turned anomaly into aspiration. At the European Southern Observatory, someone printed the story and pinned it to a corkboard above the workstation. A simple note beneath read, "The data changes physics. The questions change people." It stayed there long after the mission ended. Months later, when Loeb was interviewed for a podcast, he mentioned the email almost in passing. The host asked if that kind of message mattered more than professional recognition. He smiled. Awards fade, equations evolve, but the moment someone decides to study the unknown, that's immortality for an idea. Science, at its best, is inheritance. Not of facts, but of courage. The courage to not know and still care. To look at a universe that refuses to explain itself and say, fine, I'll keep asking anyway. Lucia represented that courage in its rawest form. A young mind daring to see mystery not as failure, but as an invitation. And maybe that's what 3I, Atlas, had really been. All along an invitation written in orbit. Not a message from beyond, but a mirror held up to remind us that curiosity itself is the oldest intelligence in the cosmos. In January 2026, Harvard received another email, this time from Lucia herself. She had been accepted into the Universidad de Chile, majoring in astronomy. At the end of her message, she wrote in English, carefully, "Tell Professor Loeb that when I find the next one, I'll send the data straight to him." It wasn't a promise of discovery, it was a declaration of continuity, because that's how knowledge survives, not through certainty, but through succession. That winter, as Loeb prepared to publish his final commentary on 3I, Atlas, he included one sentence in the acknowledgements that few noticed at first glance. For those who look up, not to find answers, but to remember how to ask. It wasn't addressed to colleagues or critics. It was for her. For the girl who turned the cosmos back into conversation. And maybe that's the point. Maybe the universe doesn't need us to decode it. Maybe it just needs us to care enough to keep listening, to teach our children that mystery isn't something to fear, but something to follow. Because every scientific revolution begins not with an instrument, but with a child who looks at the night sky and feels that ancient pull, the feeling that there's something out there worth wondering about. That's how the story of 3I Atlas truly ends. Not with conclusions, but with continuation. Meaning doesn't always arrive as a message. Sometimes it arrives as a silence that refuses to leave. 3I Atlas is gone now. No light, no trace. Its orbit carries it beyond the pull of our instruments, past the reach of reflection, into that infinite dark where observation becomes memory. And yet its absence hums, like a note held long after the music stops, because what vanished physically remains emotionally, intellectually, and almost spiritually present. The question it posed didn't disappear with it. It reverberates. In every observatory that once tracked it, the screens now show other targets, asteroids, nebulae, quiet stars. But when the late-night shifts grow still, someone always brings it up again. Not to explain it, but to feel it. The way one feels a dream that never ends properly. The object had left behind not evidence, but resonance. Not a signal, but an impression. And impressions, unlike proofs, linger. At ESA, one data engineer described it best. It was like being watched by something that never had eyes. He didn't mean paranoia. He meant presence, the strange intimacy of being part of something unrepeatable. For a moment, Earth wasn't the observer. It was the witness. The scientists who spent those months parsing numbers, aligning frames, recalibrating coordinates, they all agree on one thing: the data changed them. Not their beliefs, but their attention. They now looked at the universe differently, slower, softer, more aware of the possibility that meaning might hide in structure, not speech. A few called it the quiet revelation, not divine, not supernatural, just profoundly human, the awareness that we'd been touched by something we couldn't classify, and that was enough. Because science doesn't require a conclusion to create change. It only requires contact, and contact, in any form, leaves fingerprints. Loeb once said in an interview, "The universe doesn't owe us understanding. It offers participation." That line became a kind of unofficial epitaph for 3I Atlas. Not an explanation, but a permission to keep wondering, even when wonder feels unproductive. Because maybe meaning isn't hidden in the data at all. Maybe it's born in the act of looking. Maybe the object didn't come to tell us something. Maybe it came to make us listen. There's a kind of peace in that. A recognition that mystery isn't the opposite of knowledge, it's the frame that gives knowledge its shape. Without mystery, understanding has no direction. Without silence, sound has no form. 3I, Atlas, taught that lesson quietly, like a teacher who never spoke a word. When Tianwen-1 transmitted its last telemetry burst before turning away, the data contained one final timestamp, 03:14 UTC, just numbers, ordinary coordinates in time. But among the mission team, someone noticed 314, the first digits of pi. The mathematical symbol for infinity is contained in a finite moment. Coincidence, yes. But after all that had happened, the coincidence felt almost sacred. In the following months, scientists began referring to 3I, Atlas, not as an object, but as an event, because that's what it had become. Not a body of rock and metal, but a phenomenon that moved through both the solar system and the human psyche. A reminder that discovery doesn't just happen in space, it happens in perception. Even after it vanished, the telescopes kept listening to the region of sky it had crossed. There was no trace, no wake, no radiation, nothing measurable. And yet, strange reports began to appear in observatory logs, operators writing that they felt something familiar when aligning those coordinates again, a kind of recognition. Not physical, but emotional, like returning to a place where something important once happened. They called it the afterglow, not of light, but of awareness. In time, 3I, Atlas, became part of the quiet mythology of science. One of those stories whispered between generations of astronomers, the event that didn't prove anything, but changed everything anyway. Because sometimes meaning doesn't announce itself. Sometimes it's built in the pattern of coincidence, in the persistence of questions that refuse to die. Years later, a student writing her thesis on interstellar bodies quoted Loeb's line. It wasn't a message, but it meant something. She added her own. Meaning is the residue of attention. The universe gives what we're willing to notice. Her advisor left it untouched. Because it was true. We still don't know what 3I Atlas was. Natural? Artificial? Statistical impossibility? Maybe it doesn't matter. What matters is that for a brief moment, humanity stood together in collective curiosity, staring at a sky that refused to explain itself and loved it anyway. And in that shared silence, we remembered that science, at its heart, isn't about certainty. It's about awe disciplined into patience. 3I. Atlas is gone now, yes. But the listening remains. The recalibrated instruments, the reawakened imaginations, the students who saw in its absence the shape of their own future. It didn't send a message. It created listeners. And maybe that's the greater meaning. Not revelation, but resonance. Not arrival, but awakening. Because in the end, every mystery is both a mirror and an invitation. It wasn't a message, but it meant something. The universe never ends a sentence. It just pauses long enough for us to breathe. By early 2026, telescopes across the world had already turned outward again. 3I, Atlas, had slipped beyond reach, but the algorithms it inspired kept running quietly, combing the sky for echoes. And somewhere in the steady hum of computation, a new forecast emerged. According to the Vera C. Rubin Observatory, whose first wide-field survey was set to begin that year, the numbers were astonishing. By 2027, we may detect one interstellar object every year. Not a once-in-a-lifetime miracle, a pattern, a rhythm. The silence wasn't over. It was just beginning to speak regularly. The Rubin Telescope's LSST system, its legacy survey of space and time, was built to map the heavens in obsessive detail. Every few nights, it will photograph the entire visible sky, pixel by pixel, petabyte by petabyte. It won't just see new stars. It will catch movement, the faint, drifting glimmers of objects that don't belong here. And when that happens, 3I, Atlas won't be alone anymore. Its story will become the first verse in a long and growing poem of arrivals. At Caltech's NeoCam project, engineers spoke with a new kind of patience. Their infrared detectors, designed to spot faint heat signatures against the cosmic background, were nearly ready. And if predictions hold, by 2030, the combined efforts of Rubin, NeoCam, and Gaia's astrometric precision will yield a map not of one or two visitors, but hundreds. Hundreds of fragments are crossing through our solar system from interstellar space, each carrying its own trajectory, its own riddle, each whispering that our neighborhood was never quiet, only underlistened. ESA's preliminary models show it clearly. Interstellar debris moves through our galactic arm constantly. We've simply lacked the sensitivity to notice, like living near an ocean and hearing waves for the first time. What we once called an anomaly may soon be recognized as normalcy. And when that happens, everything changes. Loeb once wrote that the true frontier of astronomy isn't distance, it's attention. 3I, Atlas forced us to widen that attention, to reimagine what motion and matter could mean. Now, with these new instruments, that widened awareness becomes infrastructure. We are no longer waiting for the universe to surprise us. We're preparing to meet it halfway. It's strange to think, soon, every year might bring another story like this one. Another visitor slicing through our night sky, each with its own signature of impossibility. The mystery will multiply, but so will our ability to listen. And maybe that's the quiet evolution of science, not solving the unknown once and for all, but learning to live comfortably inside its frequency. At the Rubin Observatory, one researcher described the shift beautifully. The cosmos used to be a place we stared at. Now, it's a place that keeps coming to us. Indeed, the flow feels inverted, no longer a distant tableau, but an active conversation. Every new detection adds another line in an ongoing dialogue between motion and meaning. The next interstellar object will arrive, and when it does, the first question won't be, what is it? It will be, what rhythm does it join? Because what 3I, Atlas, truly gave us was context, a pattern through which the next anomaly will be understood differently. It recalibrated our sense of expectation. We now know that impossibility isn't exclusion, it's invitation. So, when the next object lights up a sensor array, well, watch differently. Not with disbelief, but with recognition. Well, remember that the unknown doesn't break reality, it expands it. And somewhere, in a data stream scrolling past an analyst's weary eyes at 3 a.m., the next wonder will emerge. Not as a revelation, as a continuation. The coming years will turn astronomy into something intimate. Each interstellar object is a visitor, each detection is a reunion. Like hearing a familiar voice across vast static, not identical but familiar enough to make us pause. And in that pause, perhaps feel it again, that strange pulse of belonging. That reminder that we, too, are moving through someone else's sky. Because if we're detecting one per year, imagine how many are passing unseen right now, their trajectories brushing past us in the dark. We are not at the center of observation, we are inside it. At a small conference in Madrid, an astrophysicist ended her talk with a sentence that stayed with everyone who heard it. Maybe these objects are not rare. Maybe we were rare, a civilization quiet enough to finally hear them. And that may be the truest legacy of 3I, Atlas. It trained us not in discovery, but in attention. It taught us that silence isn't void, it's potential. The next object is coming. Somewhere in the darkness, its light is already traveling toward us. Unseen, unmeasured, but inevitable. And when it arrives, I know what to do. Watch. Listen. Well, remember, because the universe doesn't end in revelation, it continues in recurrence, and the act of noticing again and again is how curiosity becomes culture. The first one made us question. The next will make us understand. The universe is composing, and we are finally close enough to hear the refrain. The object is gone, but silence doesn't vanish. It ripples. 3. Atlas will not return. Its path is open-ended, a trajectory that won't bend back, a line fading into interstellar dark. And yet, the echo remains, not in telescopes or telemetry, but in the people who watched, measured, and wondered. The data has been archived, the equations resolved, and the probabilities calculated. But the residue, the feeling of having touched something immense and inexplicable, refuses to decay. Because some encounters don't end when the instruments stop recording. They end when memory stops resonating. And this one hasn't. Across observatories, the logs still hold their name. Each data file, each timestamp, is a fossil of curiosity. Students learning to code their first light curves scroll past those entries and pause. For a moment, they stare at the number 3I 2025. A 3, Atlas, and realize that behind it lies a story not of certainty, but of humility. A generation from now, that story will be their first lesson, not about comets or orbits, but about how mystery sustains science more than answers ever will. At Harvard, Loeb keeps a photograph pinned above his desk, a faint blue-green streak against a black background. The Tianwen, one image that began it all. To anyone else, it looks like nothing. To him, it's proof that wonder is quantifiable. He once said in an interview, "The purpose of science isn't to close the book. It's to make sure the pages keep turning." And maybe that's what 3I Atlas was, a page turn, a hinge moment when curiosity changed direction. In the years since its passing, new instruments have risen to take its place. The Rubin Observatory, NeoCam, Gaia, and soon Lynx, each one more sensitive, each one designed not just to observe, but to listen differently. And if the predictions hold, well, soon be surrounded by these interstellar wanderers, each one another reminder that silence was never empty, only undiscovered. But still, 3I, Atlas holds its own space, the first to teach us how to notice silence itself. At the European Southern Observatory, a mural was painted on the inner wall of the main dome. It shows the outline of a comet dissolving into a waveform light turning into sound. Beneath it, 4 words. It wasn't a message, and below that, in smaller script. But it meant something. It's not an official monument, no plaque, no dedication. Just a quiet acknowledgement that meaning doesn't always need form. Perhaps that's the final paradox of 3I, Atlas, that something so solid, so measurable, ended up teaching us about the intangible, that an object, defined by motion, leaves behind stillness, that an absence became a kind of presence. We learned that data can hum, that light curves can breathe. The universe has ways of teaching that don't involve instruction. Late one night, a young researcher at ESA, someone who hadn't been alive when Oumuamua passed, wrote in her notebook, "Every time I filter noise, I wonder what I'm erasing. Maybe the universe hides its meaning there." Her mentor read it and nodded without a word, because everyone who studies 3I Atlas eventually arrives at that same realization, that listening is an act of faith. And faith, when disciplined, becomes science. The object's absence also left behind a quiet shift in perspective. We no longer ask if we're alone, we ask if we're listening correctly. And that change from existential fear to attentive participation may be the most important transformation of all. Because to listen is to belong, and belonging, in a cosmos this vast, is the rarest discovery of all. Every so often, the archives glitch, an old file from the virtual telescope network reappears in the feed. It's just a single frame, overexposed, time-stamped the 5th of November 2025. Static lines, a faint smudge of light. Nothing spectacular, but to those who know, it's sacred ground, a reminder that somewhere out there, in the dark, beyond the sun's reach, something once moved in a way that defied every equation we had, and that for a brief, the miraculous moment we noticed. The universe doesn't explain itself, it demonstrates. Every star, every shadow, every silence is a form of instruction. 3I, Atlas, was one of those lessons. A reminder that knowledge isn't measured only in understanding, but in the depth of attention we give to the unexplained. So now, when astronomers speak of the event, they do so with gentleness. They don't argue probabilities or hypotheses anymore. They simply say, it meant something, because it did. It meant that the unknown is still alive. It meant that the human capacity for wonder still exceeds our capacity for proof. It meant that silence, when heard correctly, we can change the way we see everything else. The echo that remains isn't in data or sound. It's in the pause before a question, the breath before a discovery, the quiet understanding that the universe is not a puzzle to be solved, but a song to be recognized. 3I. Atlas is gone, but its melody continues. In every observation that dares to admit uncertainty, in every student who learns to look at the sky not for answers, but for communion. Because what it gave us was not a conclusion, but continuation. It wasn't a message, but it meant something.